let's get going. Okay. I have a little cube here. This cube is actually represented by a bunch of tetrahedra.
I like those.
And I earlier already asked the question: how many tetrahedra do we actually need to represent the cube?
Simultaneously.
So how many do you need? This way to tetrahedralize the cube actually uses too many. You can actually do it with less. So and the question is how many tets do you need minimally to actually represent the volume of a cube? Is it 6? Is it 7? Is it 8? Is it 3? I don't know. I forgot. So you can play with this. So anyway, since this topic of representing space with a bunch of tetrahedra is very hard to draw on the board, because so I brought some real tets with me, so you can play with that a little bit. So it helps. Sometimes it helps to get some toys to see how these patterns work. So what did we talk about last time? Last time we talked about this issue of representing a smooth approximation function over a big triangle and achieving continuity when all these triangles have to meet along shared edges and shared vertices. And the problem there is that trying to solve the problem directly, just constructing a smooth patch over one triangle doesn't work because you don't have enough degrees of freedom. So then the idea is to take a big triangle and split it into smaller triangles. And then you have enough degrees of freedom, enough coefficients, enough polynomial pieces to actually solve the problem. And these split schemes are particularly nice if they give you just the perfect number of degrees of freedom. Okay? If you have a certain number of conditions at the corners of your big triangles, the function values, the gradients, and maybe even curvature, things like that, then you would like to have a split scheme that gives you just the perfect number of degrees of freedom that you need to interpolate all the data from the corners. That's the best possible split scheme. So this Klaftacker split that I talked about last time is one of those very, very good split schemes because, I mean, you give it at the corner points the function values and the gradients, and then all the coefficients in the interior of all these three split triangles fall out automatically, right? That's great. The other thing that's really great about it is that you do not need to store these coefficients in the background. You really can compute these coefficients for these polynomial pieces on the fly, because there are these relationships, these linear relationships between the information from the corners and the coefficients in the interior of the triangles. Right? They're all related to each other. You can compute them on the fly. You don't have to store all this coefficient information. You can compute it on the fly when you have to render or you have to do a computation with a particular triangle. Okay, so in that sense, it doesn't really produce overhead in terms of storage, but it just produces overhead in terms of procedural computations during the processing. Okay, so then I have these tetrahedra going around, play with them, and of course I brought them along because since we can take a big triangle and split it into three child triangles, we also can take a big tetrahedron and split it into, well, a certain number of smaller child tetrahedra. The question is, how do we split when we use a scheme called Klaftacker? Right? How do you do a Klaftacker split for a volume? And I just will hit on that briefly, how to do that. So last time, take a look at that. Last time we had the Klaftacker scheme, split scheme for triangles, and now I talk a little bit about Klaftacker for tetrahedra. Klaftacker for a triangle, and today I talk a little bit about the Klaftacker scheme for tetrahedra. Okay, so here we had a big triangle and three sets of information at the corners. In the volume setting, of course, we have tetrahedra with, well, four corners and information given at the four corners. And so how to split, that's really the issue, how to split a big tetrahedron into the child tetrahedra, child tets. illustration. Let's see whether I can do that. Illustro. So you start out with a representation of the entire space that you are concerned with, over which you want to raycast or compute contours or compute cutting planes, whatever. You start out with a bunch of tetrahedra. This is one of those. And for approximation purposes, at each of these corners, you have, again, function values and gradients given FCT and grad values, grad for gradient values at corners. How do you split a TET? Now remembering last time, Kate, you are admiring those TETs there, right? So we had a triangle, and we split the triangle into that configuration. How do we split a TET in an analogous fashion? Yes, Jennifer?
We do a similar thing and compute the centroid of the tetrahedron, and then for each face, that would be just the 3 points and then the centroid point.
Okay, yeah, you've read this already. That's great.
I think you mentioned it in the last lecture.
Okay, I mentioned that, huh? Okay, very close, very close. Very close. But instead of using the center or the average or the centroid of this tetrahedron, when one uses, and don't ask me why, I never figured this out why, this particular scheme, Klaftaker for TETs, uses the in-center. What is the in-center? The in-center is the center of the sphere that is the largest sphere that fits inside the tetrahedron. Huh? So there is some kind of sphere in here that you can fit, that has a center, and there is a sphere of maximal radius that you can fit into this TET. So the sphere is touching tangentially the 4 faces of the TET. So they use this center. I believe you can just use the centroid or the average of the 4 corners. I never understood why use an in-center. Anyway, so they use some point in the interior close to the middle or the center of the TET as a split point. And now, of course, this induces the first level of split. And the first level of split is connecting this point in the interior to the 4 corners. Okay. Can you still see this, what this is? This is not 4 TETs, right? The configuration, Jennifer, now is 4 TETs. But this doesn't suffice. In the volume case, you have to do much more. You also have to introduce additional split points on the faces of the big tetrahedron. All right? And so where are these additional split points that have to lie in the faces, in the interior of the 4 faces? Well, all these 4 faces have a neighbor TET, right? There are neighbor tetrahedra lying around all over the place. Specifically, the 4 faces of the big parent TET have, well, 4 neighbor TETs. So in particular, this particular guy here, this neighbor TET, also has one of these centers. And so people then use this in-center of this neighbor TET, who has also this triangle as a shared face, and connect these 2 in-centers now across the shared face by a straight line. And so this straight line, of course, will intersect that face there somewhere, and then you connect it there. Okay. So now this point on this face will induce an additional level of split, namely these additional edges, split edges on this face. Okay. So, and you do this kind of construction in all the other 4 interior TETs. So how many child tetrahedra do you get overall when you do this kind of operation? Initially I had 1 TET, I split it into 4 child tetrahedra. Then each of those 4 child tetrahedra I split into how many? 3. So it is 4 times 3. The big parent head gets split into 12 children. So these guys are again called the incenters. Incenters of spheres. Okay, and these are the spheres of maximal radius that you can fit into this TED and into this left neighbor TED. So the number of child tetrahedra you produce here, it's 4 times 3, namely 12. Okay. And now over each of those tetrahedral pieces, you construct a cubic polynomial, right? That's Krafft-Tucker. And we need to determine the coefficients, the coefficients for each polynomial, each poly over each TED. And so this then just as a note again, what is one of those cubic polynomials over one TED? The cubic polynomial poly over just one tetrahedron, just one TED. So I use this barycentric notation again. So you have one TED. This is one of those 12 tetrahedra now, okay? We have 12 of those. And if this is a cubic polynomial sitting over this volume, then I have this control point configuration. I split all of this in 1/3. These are 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. This is about 1/3. Yeah, this is 1/3. That's 1/3. So those are the coefficients. Are these all of them? No, there are also additional coefficients associated with the center of each of the 4 faces. Okay. How do I draw that? Well, here's one. Here's one. On the bottom there's one. And there's one in the back. Okay. So the poly is this function in barycentric form, u1, u2, u3, u4. And that thing is, using these barycentric coordinates, a product of ordinates b, I1, I2, I3, I4 times the Bernstein polynomial b quadruple index I1, I2, I3, I4 of an argument which is a quadruple u1, u2, u3, u4. All right, so the Bézier coefficient associated with this guy would be b3, 0, 0, 0. The Bézier coefficient associated with this guy would be b0, 3, 0, 0. If this is corner 1, this one is corner 2, this one is corner 3, and this one is corner 4, then the Bézier ordinate here would be b0, 0, 3, 0, and the Bézier ordinate here would be b0, 0, 3. That's the pattern how that index works. Cubic, right? So the highest index is 3. And this guy would be b2, 1, 0, 0, and this guy, for example, would be b1, 2, 0, 0, and so forth. You see the pattern of indexing. I can also draw the control mesh of this configuration, but if I were to draw this control mesh and introduce all the edges, then you wouldn't see anything anymore, okay? drawing the control mesh just for a two-dimensional thing, two-dimensional manifold, I can do that, but I can no longer draw this control mesh, which is really a control tetrahedron, right? So, too complicated. In the bottom, of course, the thing, just on the bottom face, the thing would look like this. Right, this is just a part of the control mesh on the bottom face. And then this structure, or this pattern, is replicated in this direction, in that direction, in this direction, and in that direction. Very complicated. So that's why I brought the toy tetrahedron, so you can play with it. So we have to construct one of these guys, each one having how many coefficients? How many coefficients are there for one tet? How many coefficients are there? Well, as many as I have drawn locations for controller units, right? In the bottom face, how many are there? 4, 3, 2, 1, it's 10, right? 10 in the bottom. The next one will have 6, the next one will have 3, the next one will have 1. If you add it up, you have 20 coefficients, okay? So these indices, I1 plus I2 plus I3 plus I4 have to be 3 for a cubic polynomial, and they have to be greater than 0. So I1, I2, I3, I4 greater equals 0. And these conditions, and therefore the restricted number of possibilities for indexing, gives you 20 coefficients. 20 coefs. Per tetrahedron. How many child tets per parent tetrahedron? 12. 12 times 20 makes 120 coefficients per tetrahedral element, right? So it's quite expensive. So, but again, the trick is you do not have to store these coefficients, but rather compute these coefficients on the fly whenever you have to deal with a particular region in space. Whatever you have to do with that region, whether it's raycasting, contouring, slicing, numerical computing, right? Okay. I know I didn't talk enough about the volume case, and maybe something still remains fuzzy or foggy, but I think you have an idea, okay, how this two-dimensional thing lifts to the three-dimensional world. Cannot resist. Okay, that is that. Now this was a scheme based on cubics. Do we like cubics? Or do we like quadratics? Or do we like quartics? What do we like better? Higher degrees or lower degrees? We like the lowest degree possible that is necessary to achieve a certain level of, well, freedom, right? A certain level of necessary degrees of freedom to achieve whatever we need to achieve. In our case, we need to have enough degrees of freedom to interpolate to data that consists of values and derivative values. So, and here talked about ways to do this with cubics. So can one solve the same problem also with using quadratics, which would be better, right? Quadratics are just better. And you know the obvious reasons. Can solve this problem? Can one also solve this problem with a quadratic split scheme, with a quadratic split scheme? I wouldn't ask this question if the answer wasn't yes, right? So, yes. How to illustrate that? The one-dimensional or univariate example. Univariate case. Again, what do? We interpolate two data on some domain, the axis x, and we have a local region where we have data over this space. Let's just call it x1 and x2, doesn't matter. And we have a function value on the left and a function value on the right, and we have derivative values there. So call that derivative 1, and here's derivative 2. And now the natural way to think about that is always to think about a cubic. I have 4 pieces of information. A cubic polynomial has, well, 4 terms, right? 4 monomials, constant, linear, quadratic, cubic. So you need a cubic to interpolate this. How can you possibly interpolate 4 pieces of information with just a quadratic? It's not possible, right? A quadratic polynomial is a parabola. It's constant, linear, and quadratic. 3 degrees of freedom. Here we have 4 pieces of prescriptions, constraints. So how can you do that? Well, the trick is you cannot do it with 1 quadratic, but you can do it with 2 quadratics. Right? That's why it's a split scheme. How do you do that? Well, you cannot force 1 quadratic to interpolate all of this unless the data came from a quadratic to begin with. No? Only then. So therefore, you just say, okay, I solved the problem in 2 pieces. I have a left problem and a right problem. No? That's the split. So you just do a split in the middle. This is a split line. Okay. And then you do another split. Now you do halving of these 2 subintervals. You have another one here and another split line here. Okay, so you split this effectively into 1/4, 2 1/4, 2 1/4, 2 1/4 in terms of a ratio. And now you want to have a curve that somewhat qualitatively looks like this. This will be a composite curve now. It will not be 1 cubic segment or arc. It will be a composite curve that consists of 2 parabolic arcs. How do you do that? Okay, well, this line still has to intersect there to interpolate to that value and that derivative. This line will have to intersect here. Okay, and now you just force these 2 circles to be connected by a line. So you just force this, and then you have this split point, a split coefficient there in the middle. And now you have a quadratic polynomial on the left, a quadratic polynomial on the right. And when I sketch these pieces, you have this piece that solves half of the problem, and you have this piece which solves the other half of the problem. But together, they solve the entire problem, right? So function value, 2 derivatives, and I want to use a quadratic polynomial, a parabola, geometrically on the left and on the right to interpolate the data. And therefore, I have 1 degree too much for each parabola, and this degree of freedom is taken away by forcing these 3 control points to lie on a line. Is it clear geometrically, intuitively how that works? Do you have a good sense for these Bezier curves? How these control polygons relate to the geometry and all of that, and to the tangents? I think you have, right? To some degree? You should. So this is now a Bezier point B0. This is a Bezier point B1. This is Bezier point B2, right? For a quadratic Bezier curve on the left. Now you have another one, which is here, which is kind of like a Bezier point B0 bar, a Bezier point B1 bar, and a Bezier point B2 bar, right? So you have 3 individual sets of 3 Bezier points defining a left parabola, a right parabola, that interpolate the prescribed data at the ends, and they are joined by force. They are joined in such a way that they also share the same value and the same tangent at the split. So that's how that works. Solve interpolation problem by constructing 2 quadratic Bernstein-Bezier polynomials. Comma, each one interpolating prescribed data data at the endpoints, at the ends. Who has not worked with Bezier curves before? Who has not come across Bezier curves in a textbook or in a homework or in a programming assignment? Who has not? You all know them, right, to some degree? Okay. Good. If this is magic for you, Bezier curves and Bernstein Bezier curves and Bernstein polynomials, look that up, okay? Very important. It's so fundamental to all what we are doing in computer-aided design, geometric modeling, computational geometry, graphics, and all of that. That is fundamental. Okay, so now, again, what was the principle? The principle was, well, the principle that we'll also apply in the 2D and 3D case. We had data at the endpoints, at endpoint x1 and endpoint x2. We wanted to use a lower degree, quadratic degree. That's the lowest degree possible that we need to interpolate with two segments of quadratic nature the data, the prescribed data, function value and derivative at the ends. And we have 1 degree left, namely this point in the middle, but it's not really a left degree of freedom because we want these two pieces to coming together smoothly so that this looks like a very smooth arc altogether. And by doing so, we have this condition that these three Bezier ordinates or Bezier coefficients have to lie in a line. So the endpoint information, again, dictates what these three interior Bezier points have to be like. That's great. So we have reduced the problem to a problem that forces us to use only quadratic polynomials. Everything is fixed. There's no degree of freedom left at the end. That's good, right? So how do we do that for the 2D case, or how are people doing that for the 2D case? And they do this with a scheme that is called Powell 7 scheme. Now this is Malcolm, right? Malcolm 7. Look him up. A very, very famous person. Very influential. Okay, Malcolm 7. Still active, maybe in his 80s now or so, but still goes to conferences and presents and writes papers. So it's pretty cool. I don't know what I will be doing when I'm 80. So Powell 7 scheme. Powell 7 scheme. How does it work? It splits a parent triangle into how many child triangles? Klafka split 1 into 3, right? So this one uses smaller degree pieces, so therefore it probably needs more pieces because it uses lower degree. Into 6 child triangles, or, and I will tell you how this case distinction is made, choosing either 6 or 12 child triangles. Okay. Case 1. Case 1 is chosen, or this splitting a triangle into 6 child triangles is chosen when the triangle is nice and when all the angles are smaller equal 75 degrees. Each angle in parent triangle smaller equal 75 degrees Again, where does the 75 degrees come from? It's an experimental number, right? Why is it not 3.48 degrees? It's frozen heuristically. Just the way it is. Probably based on a bunch of test runs they have done for numerical simulations, determining when a triangle can be split this way. So these are fat triangles. So how does this work? Case 1 split. I really have to draw it nicely so I don't get completely lost. Okay, so this is a nice triangle, as nice as it can be. And I split this into 6 smaller triangles. Again, this is the view top-down into the xy plane. We have the corner data, the locations. So this is our corner 1, corner 2, corner 3. And then it is split by putting a point in the middle. So location, and then I have to say choice of Bezier ordinate, Bezier coefficient, coef. All right, how does the triangle get split? So this guy is a corner, and this guy is typically the center of the sphere that passes through the 3 corners. Center of sphere of circle passing through the CIs, and what else? We need to split. How is it split? We take the midpoints. Midpoints are just indicated as, well, squares. Midpoints of the edges. Okay. How do I split? I just connect the corners to this center point, and I connect these edge midpoints to the center point as well. So I get this. Okay, so that is split into the 6 children. And over each of these triangles, now I construct a quadratic patch. For quadratic patch, I need 3 plus 2 plus 1, 6 coefficients, right? Each. So where are these other control points or ordinates? Here's one, here's one, and here's one. Here's one, here's one, and here's one. And here's one, here's one, and here's one. Okay, but there's something missing. There's still control coefficients missing here at the midpoints of these edges. So I draw these as maybe triangles. Why not? So these are triangle guys. So these are the coefficients we need. 6 coefficients per piece. Alright, so what else? So I have to say what the location of open square is. So these are the midpoints of edges, so just edge midpoints, mid, P and TS. Alright, and then what else? The triangles are midpoints of the edges from open square to a filled square. Okay, you see that. Bam, bam, bam. The question is, if we are prescribing the function values and the tangent plane, the gradient information at the corners, how are the coefficients for this configuration implied or determined, fully determined? Now you follow your intuition, okay? At the corners we have function values and tangent planes, geometrically speaking, right? So this information, the function value itself, implies the Bezier coordinate at the corners, right? So that's easy. This is the trivial part. At the corners, the given function value there is the Bezier ordinate, right? So the function value there, FCT value, equals the Bezier ordinate there, right? Bezier coefficient here. Okay, what is the next level of control points that are implied? Well, it's these guys, it's the circles at each corner, right? Why? Because we prescribe the tangent plane here of these patches, how the patches start at the corners, right? And that is related to, well, the derivative in this direction of this edge, in the direction of this edge, and in the direction of that edge, right? These are directional derivatives. And so above each of these corner points, you have this plane sitting there. And this plane, of course, has a certain slope in, well, these three directions. And you just evaluate this particular plane or linear polynomial sitting over this corner at these circle locations, and you get a value, right? The value of these sticks coming out of the board. So the circles are really the ones that are implied first, these guys, and you see where they are, blah, blah, blah. And the values at the circle locations are implied by the gradients, right? By the gradient data at the corners. Bezier coefficients, coefs defined by these linear Taylor expansions at the corners, defined by linear Taylor expansions. Taylor expansions at corners. Okay. What comes next? Next we have the configuration on the edges of the big parent triangle, right? And this configuration is this configuration, right? It's this. 4. This is the edge. This is one edge, right? 1, 2, 3, 4, 5 coefficients. 5. This configuration is here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4 on each edge. We have that univariate case, obviously, right? Each edge is the path's restricted to a univariate domain, one-dimensional domain, so it has to be the curve case. So these guys, the value of the Bezier coefficients at a square, have to be the average of the two closest circles close by, right? So this guy, together with this guy, define that square. And these guys define these, and these define that. So square. Edge midpoints, so the Bezier coefficient, coefs defined as average of two, I call them square values. But I'm really talking about the Bezier ordinate associated with the square location, two square values. Okay, so now we have that. What comes next? So now we have constructed all this data, and we have the squares. So now we work our way inward, okay? The progression is from the outside, from the corners, toward the center. What about the values of the triangle locations? Do you have an intuition what the value of the triangle has to be? Just follow your intuition. The triangle values, again, have to be the averages of two circles. So now I also sketch the mesh in the interior of some of these guys. So this is a mesh, right? It's in there, in one of those quadratic pieces. The mesh here is this mesh, right? So, and we have this configuration on all the 4 others as well. So these guys have to lie in a line, the coordinates, the sticks above the board. So that means the value of a triangle has to be the average of the 2 closest circles. Okay? So triangle, the Bezier coefficients, Bezier coefs defined as averages, average of 2, well, in this case, of 2 circle values. Same here, right? With the square, the square value has to be the average of 2 circle values, so this has to be a circle guy, of course, okay? 2 circle values. All right, so now the last degree of freedom that's left over is the ordinate, the stick at the center location. What is that? Any idea what that is? Is it really free or is it fixed? It's also fixed implied by the beauty of this construction. There are 3 sticks, right, coming out of the board over each of these triangles, right? There are 3 sticks coming out here, defining this plane. And because all these 6 patches have to come together in a smooth fashion, the value associated with solid rectangle has to lie in this plane. So therefore, the linear polynomial implied by the Bezier values associated with the 3 triangles imply the value at the solid rectangle. So Bezier coef implied by 3 values associated with the triangles, with 3 triangle values. Again, so there is a nice progression, right, of this construction. You first start with the corners, right? This is the corner data that is given. Okay. Then you work your way inwards, first along the edges, and you construct this data. And in the end, well, the one datum left in the middle is implied or constrained by a linearity constraint coming from these 3 values over the 3 triangles. Okay, so the last step is to get this guy to lie on this plane that is already implied by the 3 values for the 3 triangles.
So those circles, are they a quarter of the gradient, or am I missing something?
Which circles?
Those guys.
Those guys?
Yeah.
Those guys. Okay, I should sketch it again. Let me sketch it. Always have to refresh our memory where this comes from. Don't copy this. This is just to set the context again. So we had, what did we have? We have some kind of domain triangle, right? This is the big guy that gets split into 6. And at this corner, if I draw it 3-dimensionally, we have this value, and we have a tangent plane there, right? This linear Taylor expansion. So over this particular edge, we will have, if this is a tangent plane here, or the linear polynomial, a graph of it, we want this curve. Right? We need this curve to be the curve over this edge. Right? So this edge, if I represent it by 2 quadratic pieces, I have a split here, I have a split here, and a split here. So I have, there's the directional derivative, a slope, a gradient in this direction. Here's the slope here, how this thing starts, or ends. And so if this is the split line, here's the other split line, and here the split line, it's a one-dimensional case, then this function value plus the derivative in the direction of this edge defines that Bezier value. That is this Bezier value over there. Okay. coming from, or working my way inwards, coming from this corner, I get this basically ordinate. And now comes this fourth linearity constraint, or the smoothness constraint, that these two quadratic pieces, it is the piece number 1 on the left, a parabola, and piece number 2, a parabola here, are merged in a smooth way. Right? So there is solid, disk, circle, and empty rectangle. That's the configuration that we have there over each of the three edges. Is it clear again?
Yeah, so it's a quarter of the way, right?
Yes.
Okay.
Yeah.
So I'm assuming that
It's a quarter.
because
there
you're
are
working.
assumptions here when I say these things that make certain ratio assumptions, right?
So I'm assuming that that's more accurate because you're working inwards than calculating the empty rectangle first, and the circles as the average of the solid circle and the empty rectangle.
Yeah. The way I've described it, working my way from the corners toward the center, right?
Right.
It's a nice way to think about it, I believe.
So
Of course, you can write down, ultimately you can write down each of these interior control points as a function of the data at the corners, right?
Yeah.
So for the implementation, it doesn't matter whether you compute this guy first or any of the others, because each of these interior, basically, ordinates is expressible in terms of the function values and the gradient data at the corners. So, but geometrically, it is nice to think about it, constructing this tent, right? This polygonal control mesh.
So mathematically, it's the same value.
It's the same. Okay, so there's no degree of freedom left. Okay, we prescribe function values and gradients at the corners. We use 6 child triangles for the split, and all the coefficients are fully determined. Right? So the problem is not underdetermined, it's not overdetermined. The degrees of freedom we had to play with are just all taken up by the corner information. That's great. And now we have 6 quadratic patches, which is great. Why is it great? Because we ray trace, right? In our context, we are computer graphics people. We like to ray trace patches, right? So again, think of this as a terrain modeling. Problem is the terrain, right? We have data over the plane, and we have height values coming out, and we want to have a smooth terrain, even though the terrain is not smooth, but this is a different problem. So, and if you ray trace that resulting height field, well, it would be great if you have to intersect your rays with quadratic pieces. Right? Doing this, we can do that. Cubics is harder to compute the roots, right? That's one reason. But actually, all these schemes come out of the numerical or scientific computing literature. That's where they come from. Because also lower degree pieces have lower error vulnerability. Okay? Okay, that is that. Now, case number 2. Do I want to talk about case number 2 a lot? No. I just give you the idea. Usually there's a case distinction between nice triangles and ugly triangles. So the nice triangles are these. The ugly triangles are the long and skinny ones, where one angle is nearly approaching 180 degrees. Okay, that's the worst case. So, and then these cases are usually handled differently. I will not write all of this down, how you compute the values. That's in the paper anyway. So I just want to tell you how the split scheme works, how you split it into 12 child triangles. Should I put it here? Yeah, I'll put it here. Case number 2. Case number 2. Case 2 split. And that is for skinny triangles. What does it mean? I.e. triangles where at least one of the angles is greater than 75 degrees, right? I.e. for triangles having an angle greater than 75 degrees. So how does the split work? Split So now I draw one of these triangles. Okay, that is one of those cases. I just show you how it's split into the 12 children. Corner points, corner point, corner point. Now you just connect the corner to the midpoint of the opposite edge. Okay, that's the first step. And now you connect edge midpoints. And people now like to operate on this set of children triangles. I don't know why, because I do not necessarily see that the geometry of these triangles is so much better. Okay, but that's besides the point. This is the way the scheme works. So there are now 12 split triangles, right? You see them? You see the 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And over each one, again, you construct a quadratic piece. Right, so you get the idea. Over each of these 12 children, you have this control net structure. So you have to compute many, many control ordinates here. Where is it described, the formulas? I just say C power 7 paper. Or papers. Everything that I talk about is in the books anyway, right? Right? Everything that I talk about is in the books. Is it? Or are some of the things that I talk about not in the books? I hope that some of the things I talk about are not in the books, right? Or harder to find in the books, because otherwise I don't have a job, right? Do you like this future where we have remote teaching and one professor reaching 100,000 students worldwide, and there's hardly any possibility to interact and to ask questions? Do you like that? Would that be good enough? No? I want to assume that it's still better to have a life experience, right? That personal experience. I mean, the physical experience being in the same space together and that the material is presented. But some people say it's not necessary. I don't know. Maybe if I were a holographic projection here, right, then I can do that. It should ultimately reduce tuition, though, right? I mean, 100,000 students taking the lecture from one professor. Well, if everyone pays $1, it should be a great deal. That's the way it used to be, I guess, right? I mean, students paid the money for taking a lecture from a professor. The professor was charging the beginning of lecture or after lecture, right? You come to my lecture, give me your money. And so then it just got into the big system, and now we just pay the money into the big system, and the big system pays the professor somehow. Right? So if you're a super professor, a great professor who's just very popular, and who really can reach the masses, I mean, if I reach 100,000 students worldwide, for each lecture, every student can pay $1. $1 is nothing, right, for the individual. But for me, the professor, getting $100,000 for each lecture, and I give 20 lectures per quarter, that's $2 million. That's great. I'm happy to give half of that to the university, right? Anyway. But what about all the other professors? I don't know. I think Stanford and MIT and Harvard are really moving aggressively forward in that regard. So there's an interesting article by President Hennessy, John Hennessy, who wrote this classical textbook about computer architecture, the textbook in edition number 27 or whatever. In the latest IEEE Computer magazine, I strongly suggest to read it. IEEE Computer magazine, you can get it online, right? John Hennessy talks about this future with this digital experience, remote experience, education via the internet. So what comes next? Next comes another scheme to represent space and decompose space and tessellate space and so forth. This is a Voronoi diagram. I will talk now about the Voronoi diagram. What do I want to talk about? Not a lot tonight. There are entire books written about Voronoi diagrams, which are also known in other disciplines by different names. Okay, do not assume that these Voronoi diagrams only are called Voronoi diagrams. They're also called Dirichlet tessellations or Thiessen tessellations, because these different people developed the same concept at roughly the same time. And then people referring to their papers gave these methods the names of the original authors of these presentations of those methods. And so since they presented these ideas around the same time, some methods were, some of these papers were then referred to as Thiessen, Dirichlet, or Voronoi, right? And even other names. Original concept, one of the original motivations to come up with this concept of Voronoi diagrams was to come up with maps assessing the influence region around a particular village or town. Where do I go shopping? When I want to go shopping, I go to the town that is closest to me. That's this concept, right? What is the influence region? So when you go shopping and you buy your next Armani suit, you cannot go to Sacramento. Maybe there is no Armani suit in Sacramento, even though that's the closest bigger town. You have to go to San Francisco, right? Also, if you want to go shopping next week and you want to buy your Lamborghini or your Maserati, maybe you cannot buy it in Sacramento, even though there's a Maserati shop, right? You know that. So, well, you can go to Sacramento. You always go test drive, right? You have to do that. Just have to dress up appropriately. I want to test drive. I like to do that, just test drive. When the new models come out, I need to test drive. So, not that I can afford them. So, Voronoi diagram is the next topic. Voronoi diagrams. What do I want to talk about? I want to talk about some of the most important characteristics and two main approaches to construct them. Okay. So an example, start with an example. Okay, the Voronoi diagram for 2 points. What is the Voronoi diagram for 2 points? You all know them, right? The perpendicular bisector. Boom. Okay. This is the Voronoi diagram. Okay. So this guy has a name, and this is a famous term, perpendicular bisector. What is being bisected here? Well, space is bisected, right? Infinite space is bisected into two half spaces, this half space to the left and the half space to the right. These things are called the sides, okay? Sides. And this is called the tile of that side. All right. 2 is boring. What about 3? What does a Voronoi diagram look like? I just draw it, okay? Your eye sees it anyway. It looks like that. Okay? So I call them side number 1, I call them side number 2, both face x's, 4 points with x and y coordinates, in side number 3. And there's an additional point where these edges come together now, right? Here there is no additional point there, but as soon as I have 3 in general, there's this additional circle point there, okay, which will have a name too. So, okay, that's that. Now I do many more points, and I just give you the result, what the Voronoi diagram does look like when I give you these, or this configuration. I cannot give you more complicated configurations because then I get confused and I cannot draw it anymore. Okay. This leads to a beautiful structure that I always love, namely this structure. Okay. That's the Voronoi diagram for this beautiful arrangement of sides. Beautiful because the tiles come out to be beautiful, okay? So here we had 2-point example, here we had a 3-point example, and here we have a many-point example. So, and here we have these additional points there, right? These are not original sites, but these are special points. So what do we need to know? We need to know the nomenclature that the people use in the books. So this particular area here is called a tile. Okay, I call it tile I. This point would be site or point I. Xi is site I, and Ti is the tile of Xi. Okay. And now characteristics. What do you see, or what do you assume that this diagram has in terms of characteristics? One has to prove them, of course. Characteristics. What are characteristics? Many of you have already taken computational geometry, right? So, shoot, give me some characteristics. There are a gazillion.
So, any point in a tile of the sites, the site in that same tile is the closest.
Right.
Yeah.
That's also the definition of the thing. Yeah. So, in the sense, characteristics or the definition that produces this tessellation def. Every point xy inside Ti has xi as closest point relative to all the given sites, xj. Okay? All points x arbitrary location in tile I have xi as the closest point among all sites. Have xi as closest site. That's it. Okay. More characteristics. These things, the tiles, they are concave. No, they're not concave. They are convex. Why is that? The Warner diagram itself is an intersection of convex regions. The intersection of convex stuff gives you something that is convex. Okay? So this construction going from 2 to 3 to 4 to many ultimately means that you intersect all these diagrams with these pieces of perpendicular bisectors. Right? And so since these two half spaces are initially already convex, right, even if they are open spaces, the intersection of all these half spaces that get inserted over and over again will lead to the insertion of more and more convex tiles. Okay, so that's a characteristic. So characteristic is all tiles, even these open ones, these infinite ones, are convex. All tiles are convex. Okay, what else? Look at these additional points that are put in there, the circle points. Do you see something that holds for them? Could you make a statement about the characteristic of the circles? How many edges come together at a circle? 3. Always 3? In the picture that I've drawn. Therefore, maybe always. I mean, the first case where the circle occurs is this situation, right? There's 3 edges coming together. And in this one I've drawn, the circles always have 3, right? So these are the Voronoi vertices. That's what they're called often. Voronoi vertices. So these are not the sides. These are the dual points. Voronoi vertices have, and this is the valence, right? How many edges run into them? Have valence 3. Always or not always? For sites in general position. Okay? So that means always. With a computer, you can always force points in general position by just perturbing everything. Add or subtract a random very small epsilon. Okay, that's what I always did in order to make my programs work, because you always have to worry about the degenerate case, divide by 0 and whatnot, and dealing with things when things become collinear, co-circular, and coplane and all of that. In order to avoid that, you just make everything wiggle a little bit by adding or subtracting some very small machine precision epsilon, right? And then everything works. Okay. Now what? Now I should talk about the ugly cases, namely the degenerate cases, when these characteristics are not satisfied. But again, these are countable infinite degenerate cases. So let's see. But I'm just saying but. Okay. Bam, bam, bam. Okay. What's the Waldo diagram for one of our simplest arrangements of points? The simplest arrangement of points is taking points from a Cartesian mesh, right? The mesh on the floor. The mesh on the floor is a Waldo diagram, right? Okay. All right. So what about this? So the sites on the floor, there are some sites on the floor that I see where the arrangement is very regular and uniformly spaced, blah, 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 and all of that. So what is the Waldo diagram for this beautiful, beautiful point set? You assume this is a nice case to handle, right? For Waldo diagrams, no, it is not. This is an ugly case for the machinery because it's degenerate. Why? Because, well, the bisectors are these. Whoops, and it's degenerate because this characteristics about the valence of these Waldo vertices no longer holds. Okay, here we have now 4 edges of the Waldo diagram coming together at the circles. It's bad. So in a case, the simplest case in terms of the arrangement of points leads to an ugly case to construct the Waldo diagram. But again, if you were just to shuffle these points a little bit, perturb them a little bit, then you don't have that. Right? This is only in the mathematical ideal situation. Why is that? What about this? Okay, I give you the answer why that is. I give you co-circular points. I give you a bunch of points, a bunch of sites that lie on one and the same circle. An arbitrary number of sites. They just happen to lie in a circle. Again, you want to assume that it's a beautiful case, right? No problem. What will be the Waldo diagram for that? Perpendicular bisectors, right? This is the most horrible case. The perpendicular bisectors all we meet where? If the original sites all lie on one and the same circle, then this is the Waldo diagram. It's numerically horrible because now this valence is really exploding, right? The valence here in this co-circular situation or arrangement is, well, the number of sides that are co-circular. Here we have, of course, 4. In this beautiful Cartesian pattern, we have 4 points lying on a circle. Therefore, we have these 4 bisectors coming together in that valence 4 point. Here we have many, many more points lying on the same circle. So all these bisectors come together in the same. When you do this numerically with a machine, of course, they will have all kinds of ugly numerical problems, right? But you have to handle that. Okay. So now I want to talk, very briefly, just so you're aware of this, there's beautiful stuff that you can do. The mathematical ideal of a point has 0 volume, has 0 region, has 0 measure, right? But instead of talking about points as my primitives to construct a tessellation for, I can also have this. I can have disks. I have a disk. I have really, these are solid disks, these are not points. Okay, these are really regions with more than 0 area. Okay, so there is also, of course, a definition of a Waldo diagram for stuff like this. right, for a bunch of disks. What is a Voronoi diagram? Well, the definition of Voronoi always meant, well, I'm inside tile I when I'm closest to object I, now no longer point I, but object I, than to any of the other objects, right? So you need a notion of distance to an object, which in the case of a disk means, well, perpendicular distance to the circle, right, around that object. When you actually compute that thing, it turns out that now in the case of circular disks, the bisectors become hyperbolic arcs. You can derive that. And so these will be curved creatures, and they will look like this. Just have to believe me. So everything in this side is closest to that. Everything in this side is closest to that, and everything in this side is closest to that. So these arcs always are curved toward the smaller one of the two. Oh. Curve this way. Now, not only can you do that, but of course you can also define a Voronoi diagram for this. Right? You can define a Voronoi diagram for that too. You have a bunch of objects or regions in space, and you ask the question, okay, how do these objects tessellate, separate space? Well, again, the inherent definition of Voronoi tessellation is I belong to tile I if this object I is closer to me than any of the other objects, right? So you need a meaningful definition of distance to an object. So again, you probably get a tessellation like this, right? Something like that. Huh? All right. Just want to mention this. The concept of Voronoi diagrams goes way beyond just point sets. Okay, it goes to objects, right? Cities. Voronoi diagrams. So see that where it goes again. That goes the geographical context. That's where it came from. To have the to come up with good ways to come up with maps to show the influence region of villages, cities, metropolitan areas. Okay, now comes the construction. How do we construct as computer scientists? We construct in two ways. Way number one and way number two. The Towers of Hanoi, how did we program that in high school? And our high school teacher said, well, this is the way I do this with my hands here on the desk, Towers of Hanoi, right? You all know this. And then you can program that with your Casio iteratively or recursively, right? How about this concept of iterative construction and recursive construction for Voronoi diagrams? How does it apply? Well, the iterative solution always says, if I have a problem that requires me to perform n things, n steps, n operations, then I just do it one by one. Right? For the first one, for the second one, for the third one, for the fourth one, until I'm done. The iterative or recursive thinking always says, okay, I'm given a problem, but I can only solve this problem for a small number of configurations, right? If the configuration or the problem space I'm given is very small, it's my base case, then I'm done. I can do it. Otherwise, if this problem is way too big, way too complicated, then I have to split it into subproblems. And I solve subproblem A, subproblem B, and then I merge the result. Right? And then I recurse down, and then I go back up. Right? That's the concept of recursion. So again, with the Voronoi diagram, you can do it also both ways. And VD construction, Voronoi diagram, right? Voronoi diagram, VD construction. Okay, so one is iterative, meaning we insert point or site one by one and update after each step of insertion the diagram. Iterative, and the other way is divide and conquer or recursive, right? So iterative, recursive, that is of course divide and conquer approach. Divide and conquer. Conquer. All right. Not a lot of time, so therefore I do it for a very small number of sites, and hopefully you will appreciate the general thinking. So 1, okay. 2 is the simplest, right? So I have the Walner diagram for 2 sites in place. Okay, that is my current state. I have inserted point number 2, and the result, Nick, is the first meaningful Walner diagram, right? Okay, and now I grab point number 3 and I insert it. Okay, point number 3 gets inserted here. Okay, so this is a new guy. So new guy is always asterisk. What happens at that point if I do this update iteratively? Update iteratively means I have to change the Walner diagram, right? So the new Walner diagram looks like this. It has to go here and up there. What is going on there in terms of the algorithmic steps? I just tell you, it is all in this book by Preparata Shamos. Preparata and Shamos. Read this book. And memorize it. So, first step is I have to determine the tile inside which the new point lies. Okay? This point lies in the tile of this guy. Okay? Therefore, I can construct the bisector between the new point and the side inside which the point lies. Right? So I get this one. Okay, so this is a new bisector that I construct. I give this line a direction. Now what happens when this line is moving around in space happily? What will it do? It will intersect with an existing bisector, right? So this point, we call it the Walner vertex, right? It's an intersection point. It's one of those circles. Now, what happens effectively if I'm traversing on this? Well, I'm entering a new tile. I'm entering the tile, the domain of this guy. So therefore, that means I now have to construct the bisector between the new point, this guy, and this side. And so the bisector for these looks like this. And this goes up there to infinity, right? That's it. Not quite. I have to update my diagram, namely I have to remove this old piece. Okay? So I just explained the algorithm by doing the example. Again, I have 2. Okay? New point comes in. First step, new point lies in this tile, therefore construct bisector with this guy. Bisecting line will intersect with other bisecting lines already existing. Intersecting points become circles. When I intersect, I enter a new tile, therefore construct tile between bisector between new point and the owner of this tile that I'm entering, and I get this one. Done. I no longer intersect anything because I'm happily going off to infinity, but then I have to clean up my old diagram there, and I have the new tile. Now the new version is this, right? Something like that. So that's the iterative version. Is this good? Is this efficient? Is this nice? Is this easy? Think about that. How expensive it is in terms of data structure, and I mean data storage complexity and time complexity. How many steps? So the other part is 2. I'm very stupid and very dumb. I only know how to construct the Walner diagram for 2 points. That's all I know, right? That's the base case or the anchor, right? So base case is give me points. If you give me 2 points, the Walner diagram is the one given by that one bisecting line. Boom, done. If not, if you give me more than 2 points, then split the pot of points into pot A and pot B, construct the Walner diagrams for pot A, pot B, and then merge the partial results. That's the thinking, right? That's the recursion. So, so the general idea is no, I know how to construct the VD for 2 points, otherwise recurse. Know how to construct the Walner diagram, VD for 2 sides only, semicolon, if more than 2 sides given, then break it down into 2 subproblems and then conquer the partial results. Otherwise, split problem into two subproblems, and I'm just saying and merge, okay? Merge the partial results and merge. The simplest way for me to show that might be this. Okay, so I give you 4 points. Okay. I give you 4 points. The 4-point case is already way too complicated for me to do it in one step. I can't do that. I only know how to handle 2 points. Okay. Therefore, if 2 points are given, construct the one line and done. Otherwise, take half of the chunk of the data and construct VD, and then take the other chunk of the points and construct VD and then merge the two results. Okay? So I take these two guys and construct the VD, the Voronoi diagram, and I take these two guys and construct the Voronoi diagram. And then I have to merge the result. When I take point 1 and point 2, so this might be side 1, side 2, side 3, and side 4. So step 1 is VDs for two sets, right? For the set x1, x2, and separately the VD for the set x3, x4. Okay, and then I merge. Okay, so the Voronoi diagrams for these two subsets, each consisting of 2 points, are of course these two lines, right? This guy and this guy. These two lines define the independent Voronoi diagrams. And now comes the merge step. The description of the merge step in the Preparata Schemas book takes up about 20 pages. It's one of the most complicated geometric constructions there is. Okay? So, but it's exciting. It's a great proof for qualifying exams. Okay? Have you read the 20-page construction of the merge step? Okay. So, all right. So what happens? How do you merge? Well, what happens here? There's a Voronoi diagram here, right? The merge step gives you this. The merge step has to introduce this edge. Right? Then there has to be a bisector here, right? That bisects these two half spaces, and there has to be something like this. Okay? And then something has to be cleaned up. Something has to go. What goes away? What is no longer necessary? This stuff goes away, right? Vanishes, and this stuff goes away, vanishes. Right? And the VD, the Voronoi vertices will become those points, right? Right, so the result that you want is this result, of course. These are the 4 points. And the Voronoi diagram is this stuff. Right? And boom, and boom. That's it. I mean, I can see that with my eyes, but the dumb machine cannot see that, right? The dumb machine has to do it for these 2 points, for those 2 points, then merging it. So the dotted line is the result of the merge step, which is very complicated. Result of the merge. So you should program this, okay? But the merge step is very hard to program. Even harder for 3-dimensional Voronoi diagrams. You can think about all of the generalized, right?
So I'm assuming there's a special case for odd numbers of sites as well?
No, this doesn't. It doesn't have to be an even number or power 2 integer. It doesn't matter. I can give you 37 points. Okay, so 37 sites. 37 is too big. Put 20 points in port A, and the remaining ones in port B, and solve that. You only have to recurse back to the anchor case or the base case of 2, right? Or actually even 1 if you want to go there.
That's what I mean.
You can go down to 1, okay, if that is your base case. Voronoi diagram for 1 point is just the infinite space around it. All right, so far so good. I think you want to think a little bit more about the iterative insertion, how you iteratively insert, because that will be the one that you need to implement for your third project, iterative insertion of sites one by one. But you also are invited to look at the description of this divide and conquer approach for Warren diagram construction, one beautifully discussed in this book by Preparata Shemos, Computational Geometry. I'll see you on Tuesday. Anyone still needs to sign up for demo time? Kevin? Okay.